An electron of charge magnitude E and mass m enters a uniform magnetic field B perpendicular to its velocity and follows a circular path of radius r. Determine the kinetic energy of the electron in terms of E, B, R, and m. So here's a little diagram of the situation here. And these crosses represent the magnetic field, which is pointing into the page. So the magnetic force exerted on a moving charge is given by this vector equation, and the direction of the force is given by the cross product of the velocity and the magnetic field. But for this problem, we have to be kind of careful because this is an electron that we're talking about, so its charge is actually negative. So the direction will be opposite the expected magnetic force on a positive charge. So we just need to keep that in mind. And if we use the right-hand rule on this electron here, then if you do V cross B, then the force would point up this way. But since this is a negative charge, we flip it and it ends up pointing this way. And you can do the same thing for so this force pulls the electron sort of in this direction. And you can imagine maybe a few moments later, it's at this position and heading this way. And here, if you do the right-hand rule again, then you'll see that the force points inward. And you can sort of see that this force points radially inward and is perpendicular to the velocity at all times, so it follows a circular path. And so we want to determine the kinetic energy of this electron. And we know that kinetic energy is dependent on velocity. So maybe we can figure out the velocity that this electron is traveling with. So from this force equation, we can find the magnitude of the force. And that's just given by E times V times B times the sine of theta. And theta is the angle between the velocity vector V and the magnetic field. But here it says the magnetic field is perpendicular to the velocity. So that means that theta is 90 degrees and the magnitude of the magnetic force is just E times V times B. Since sine of 90 degrees is just 1. So this essentially just disappears. And now we can use Newton's second law. It says that the net force acting on some object is just equal to its mass times its acceleration. And then let's apply this in the radial direction. So the only radial force is this magnetic force that's pointing radially towards the center. So we have that this force, which is the magnitude is given by EVB, is equal to m times a, and this acceleration in the radial direction is just the centripetal acceleration, which is just v squared over r. And so this essentially just simplifies to this expression here. And we want to solve for v, because if we know v, then we can express the kinetic energy in terms of v. So if we cancel this out and multiply both sides by r and divide by m, we get that v equals ERB over m. And so from that, we know that the kinetic energy is given by 1/2 times m times v squared. And if we just plug in v, we can simplify this. So this becomes m over 2 times e squared r squared b squared over m squared. And this m cancels. And our final answer is just e squared times r squared times b squared over 2m. Okay, so now we have an answer, but we can do one more thing to see if our answer is on the right track. And so we can analyze the dimensions of both sides of this equation. So we want to see if the units of the kinetic energy K are actually equal to the units of this expression here. And if they're not, then we have definitely done something wrong in the derivation. So let's go about finding the units of this expression here. So the units of this are just the units of each of these individual variables, and they're all squared and multiplied together. So the units of E are just coulombs, since E is a charge, so it has the units of coulombs, and we square it. The units of R, R is a radius, so it has the units of meters, or length. And B is the magnetic field, which has units of Tesla. And this bracket just means the units of B. So the units of B are Teslas. And we know earlier that the magnitude of the force is given by QVB times sine of theta. So B, we can use this to find the units of B. If we rearrange this, the units of B are just the units of this here. So that's just force has units of Newton, and Q is a charge, has units of coulombs. V has, oops, I accidentally did another B in here. And V has units of meters per second. And sine of theta is just a number, so it doesn't matter in terms of our units. And we can simplify this a bit. And that's the unit of a Tesla, which is, or the Tesla is equivalent to this, and a Tesla is a unit of the magnetic field B. So we can plug that in as well for the units of B. And in the bottom, 2 doesn't have any units, it's just a number, and M has units of kilograms. So now, if we just simplify this, these cancel, since they're squared. This becomes meters squared and cancels with this one. And we have Newton squared times second squared over kilograms. And if we pull out one of the Newtons, I can write it here, and we can actually expand this Newton, this unit. So this becomes kilogram times meters per second squared. And notice how all of this cancels out to give a final unit of Newton times meter. And a Newton times meter is really just a force times some displacement. This is the same unit as energy, which has units of joules. So the units on this side do align with the units of kinetic energy, which just means that both sides have units of joules. And so that sort of lets us check our answer a little bit, and it's something that you should do if you have extra time. And it turns out that this is the correct answer to this problem here.